less than x greater than 0 less than 1, and -1 for x greater than or equal to 1. Just wanted to say that this is the easiest problem moving forward. You will not see something easier than this for the rest of the semester. So that's why we had like 5 or 6 examples. So right away, I can differentiate this function because I'm asked to differentiate it. And I get 2x, I get 1, and I get 0. What I don't know is if to include these points. And I'm not going to include them for now. But I know for sure that this function has a derivative everywhere, maybe except at 0 and 1. I don't know. But I can immediately differentiate it. I know the derivative of this, I know the derivative of this, and the derivative of this. Many of you didn't even write this, and I don't understand why. Because you know how to differentiate these. We know differentiation rules. You don't have to do anything. Then, of course, what I'd like to do is change this into -infinity 0, change this into 0, 1, and change this into 1 to infinity. Now, when you look at this and you see that nothing is missing, I don't want to see something like this, which many of you did. We've never done this. If the function is defined everywhere, if you want to write it, you have to write it like this, not like this. What's the point? 0 is here, but it's not here. 1 is here, but it's not here. We don't write this unless there is a gap. If there is a gap, like from -infinity to 0, union 5 to 6, yeah, I have to use this because there is a gap between 0 and 5. But if nothing is missing, we never write it like this. Okay, then I create the table. And the table has to have -infinity to infinity and has to have these thresholds. The bracket and the parenthesis and the parenthesis and the bracket. And we know how to do this because we've done it so many times before. Okay, I write myself a note. Between -infinity and 0, I will be using x squared minus 4. Between 0 and 1, I will be using x. And between 1 and infinity, I will be using -1. They cannot overlap. They cannot overlap. This will not be a function if they do. Write it down on paper so you don't forget if that's helping you. This has to be a quadratic function, so I will plug in -2, and when I plug in -2, I get 4 minus 4, not -4 minus 4 as somebody wrote. So we need to know that when we square -2, we do not get -4, but we get 4, and 4 minus 4 is 0. When we plug in 0, we get -4. When we plug in 0, we get 0. When we plug in 1, we get 1. This is a linear function. And anything else here is -1. Just that's all I have. So then when I graph it, I will graph it again in 3 colors. You do not have to. But if you graph a function, a graph that is not a function, it crosses like this, and there is another something like this, I cannot give credit for this. This is not a function. So next, I'm going to use green for -2, 0, which I know how to graph. It's quadratic. I'm done. Now I graph in the middle. This is a linear function, 0, 0. I don't know if this is a good color. So 1, 1, right? Open, open, graph, done. And now I graph the rest at -1 all the way. So just make sure that this is open, but this is closed. As you see, the green does not overlap with the pink and does not overlap with the brown. You cannot extend this, you cannot extend this, you cannot extend this. If you extend these, I can't give credit. This is not a function. By the vertical line test, is not a function. And we talked about this Again, if you want to review the videos before you do anything else, you're going to be able to teach this class next semester. If you don't do it, you're always going to feel behind and you're going to make me cry. Well, that's not important, but okay, so this is my f of x. Obviously, there is a jump at x equals 0 and at x equals 1. So this is the derivative. There is nothing I can do here. I cannot close these or put the equal symbol. Obviously, because the function is not continuous at 0 and 1, it cannot be differentiable. The derivative does not exist at 0 and 1. So this is it. There is nothing else I can do there. And here we were also asked to find the range from -4, right here, is the lowest point, -4 to infinity. That's it, just 3 minutes. So write this note to yourselves. When you're finished with the graph, ask yourselves, okay, is this a function? Yes, it's a function. Good. Next question. Is there a next question on this, or is there a question on this right now? Okay. Next question. Is there anything else you want to work on? Anything else?
I didn't get to finish the last one, but I still kind of wanted to know.
You mean the extra credit?
No, 11.
What was 11? Yes. So again, this is just a couple of lines. So we are given the cost, which is 3 the square root of x plus 80x, and we are given the revenue, which is 1000x, and we're asked to find the derivative of this function and then evaluate it for 10. This was the question. Okay, so first I have to create the function. As we did in class, we had examples like this. So please review the notes, review the videos before you do anything. And take notes, again, summarize. So the profit function is revenue minus cost, 1000x minus 3 the square root of x and minus 80x. These are like terms. So I'm going to write 920x minus 3 the square root of x. Then I will create this function, which is 920x minus 3 the square root of x over x. As we did, I separated into two fractions, so I can simplify. 920x over x is 920 minus 3. The square root of x over x is x to -1/2, because it's 1/2 divided by 1. So x to 1/2 divided by x to the first power is x to 1/2 minus 1, which is x to -1/2. That's all. And when I differentiate this, there is really nothing, right? P of x over x prime is, this is 0. 3 divided by 2, x to -1 minus 1. Done. And now when I plug in 10, I have 3 over 2 times 10 to -3/2. I got, let me see my calculations here. What did I get? I got $0.05 per unit. Again, I'm begging you to redo the notes. I'm begging you. I don't mind begging you. As I said, I gave myself a new nickname.
I have a question.
Yes.
For that question, why did you use the p x over x?
Because I put it in uppercase or different color. The average profit function is p of x over x.
So when it asks for things like average profit, we need to input it as that?
Yes.
Okay.
So the average profit, let me look back and I'll tell you where we discussed this in 1.8. Let me find it so you can see it. It was it in 1.8 or in 1.6? I'm gonna find it in a minute, so for everyone to look at. Let me see. Was it? Yeah, I'm correct. It's in 1.6. Yeah. So let me show it again. And we did this in class. If you will review your notes, please, I'm begging you. Okay, so if you punch in 161, you will see this is what we discussed. Here it is. The average cost, the average revenue, the average profit. Good. Other questions? Anything you'd like to ask about any question? Anything? Anything else? Oh, actually, I wanted to go back to when we get there to 201. Okay. Is there anything else you wanted to work on? Anyone? Okay, perfect. So in that case, we will move on to chapter 2. In chapter 2, we only look at 3 sections. Okay, so chapter 2, only 2.1 through 2.3. And we deal here with exponential and logarithmic functions. Of course, and their derivatives, etc., etc. So first, in 2.1 is just algebra. Let's review our functions, the exponential and log. The reason why you see these together at all times in algebra and calculus is because they are inverses of each other. Inverses of each other. So the exponential is the inverse of log, and log is the inverse of the exponential. Here's another indication. See this button here, log, and the blue back function, 10 to the x. These two are inverses of each other. ln, natural log, and e to the x, they are inverses of each other. Easy to remember. Also, these two are inverses of each other, as you see. Also, these two, but you're not responsible for trigonometry. But this is an indication. These two are inverses of each other. These two are inverses of each other. These two are inverses of each other. Okay. So let's refresh our memory on their graphs. So there are two shapes here. Of course, two shapes here. Why? Because the exponential function looks like this, a to the x, and this is the base. The base cannot be anything but either between 1 and infinity, not 1, of course not infinity, what's infinity, right? It's a symbol. Or between 0 and 1. So what I'm telling you is, although 0 to the 4th power exists, is 0, or 1 to the 3rd power exists, is 1, or -3 to the 2nd power exists, is 9, these three bases, 0, 1, or negative, are impossible for this function. And you can say, wait a minute, if 0 to a power exists, 1 to a power exists, negative numbers to a power exist, why can't I have them here? Because of this function. This function will not exist if the base were 0, 1, or negative. So that's why they were excluded, period. So if we have a tiny base, there is a shape for this function. If we have a big base, greater than 1, we have a different shape. So I'll start with this one. This is what we've been going through since 2020. I never thought I would say that. It's this function, relentless growth. Today, 10 people are sick, but 3 days later or 2 days later are 10,000 sick, and then 100,000 sick, and then so on and so forth. Fastest raise, increase. So this is a to the x when a is a base greater than 1. Terrible. That's why they used to say, let's flatten the curve. Flatten the curve. Hopefully. We are there, I hope, by now. Okay. Now, when the base is tiny, so as you see, this function is always increasing. When the base is tiny, this one, like 0.2, 1/2, 1/3, 1/16, that graph is this. Both of them cross at 0, 1. So this is a to the x, but a is tiny. Now, this is also the same type of graph with 10 to the x or e to the x. These are the two functions that I just showed you in the graphing calculator. So here it is, 10 to the x, right, and e to the x. So if you want to graph this, you don't need to. We just graph them. But if you want to graph e to the x, here it is. As I said, nothing new. We just graphed both. The shape is the same. That's not what I meant. That's not what I meant. What did I mean? I meant this. No, that's not what I meant. Okay. Okay, so when you click on graph, let me make sure that I have the standard viewing window. You're going to see one is in blue and the next one is in red. This is a hoax. So what I'm saying is, no, these two graphs will not become the x-axis. No. So please make sure that you will never copy a graph like this. Okay? No, they will not become the horizontal asymptote. So indeed, this is a horizontal asymptote, y equals 0. Indeed, a horizontal asymptote is y equals 0. Correct. But they will not, eventually we say, very, very far away, but they will not touch the horizontal asymptote. Eventually they may, but definitely not here and become the same with the horizontal, with the x-axis. No, no, no. Eventually at negative 10 billion, but not here. Okay? So please don't copy a graph that you see from the graphing calculator. Okay, now, the most important one is e to the x, which is called natural exponential function. And this is called common exponential function. You saw both of them in the graphing calculator. Now, if I were to ask, since this is the same graph with e to the x, this is the same graph with 10 to the x, slightly different, closer to the y-axis or further away, but the shape is the same. Now, if I ask you, what is the limit of e to the x when x approaches negative infinity? Look at the graph. And the limit of e to the x as x approaches positive infinity. Look at the graph. And I'm sipping a little bit of water.
0.
Yes,